Okay,
Yeah,
fine.
it is visible.
Oh, oh, you- just let me know if my voice is not audible. I'll stop in between and I'll try to improve my vocals.
Yes,
Okay.
yes, yes.
Okay. So thanks a lot for the warm introduction. And I was given this privilege by Dr. Rajaram. He asked me to enlighten you on this I mean, how to design the anchors for these non-structural elements, especially. I mean, this particular chapter is added in the latest version of our IS 1893 2025. So before I venture into these particular details, let me just give you, the few add-ons which we have for this present code. See, as many of you might be aware, this is actually the seventh version which we have, the seventh revision, and all the six revisions which we had are now outdated, and this is the latest version which we have. And see, the hazard maps, the hazard zones, they have also been updated a lot. We are using this probabilistic estimation of hazard map rather than deterministic estimation, and it is data-driven model also. That's the reason we got a better precision of hazard map now. And then we also have the response spectra. I think you guys might be knowing response spectra is how a band of uh, which is exhibiting some natural periods. So you have the natural period on the x-axis, and you have natural period on the x-axis, and you have spectral acceleration, which we call it as SEA. You have a spectral acceleration of y-axis. The previous codes, I think it was limited only to 5 seconds. But now in the present code, it has been updated to 10 seconds, which means you can estimate the amount of acceleration, which is lateral acceleration, which is coming onto our building, even if the time period of this particular building is 10 seconds. A thumb rule to estimate the natural period of the building is you can just divide the story with respect to 10. For example, if you have a single story building, 1 divided by 10 is 0.1 second. And if you have some 100-story buildings, 100 divided by 10 is 10 seconds. It's going to take some 10 seconds for the building to vibrate. That's called as natural period of our buildings. And uh, there are a few more provisions which are added, like which I'm not going to emphasize much. Some special emphasis has been given on soil structure interaction also, which we call it as SSI. It means how loyal is the soil towards our structure and how the structure responds to any intricacies in the soil. For example, let's say the soil settles down when you build a structure on that, and when there is some settlement issue, will there be any additional amount of movements in the structure or not, and thereby how does the structure respond, and then how does it respond even to the soil, and it goes in a loop. So that provision has also been added. And we also have this liquefaction evaluation. See, typically we have this pore water pressure. Any soil will have some safe bearing capacity. With increase in pore water pressure, what happens is the safe bearing capacity comes down. So we have this sort of liquefaction problems during earthquakes and all. That so some special clause, relating to that particular liquefaction problems were also addressed. And coming to the aspect which is given to me, the clause which is given to me to explain, there is some special provision in chapter 10 where they asked us even to emphasize on non-structural elements. This category comes under NSE, non-structural elements, which means they don't participate in load transfer. Typically, you have load transfer members. You have slab load is transferred to beam, and from beam to column, and from column it is transferred even to the foundation and all. But they are called as structural elements. But here, special emphasis is made on this non-structural elements. They are only for functionality purpose. You have a fridge, you have a refrigerator, you have piping lines running in your buildings. They typically don't participate in load transfer, but at the same time, they also get damaged during earthquake. And what can we do to them to create an earthquake resilient society? Earthquake resilient society means even if there is an earthquake disaster, it needs to bounce back very quickly. So that's the reason this particular provision has been created. See, the very purpose of this code book is to make as many people as earthquake literates. They say that no climate literates who can understand climate change. They are called climate literates, and who can understand this engineering seismology are called as earthquake literates. So we just want to be earthquake literates. And there is also a famous saying. I don't know whether you heard of it or not. It's not the earthquake which kills people. It's the lack of awareness of earthquake that kills people. See, for example, you are standing on an open ground and suddenly there is an earthquake. Nothing is going to happen to you because there is no structure, which is going to fall on our head or anything. But whereas if you stay in your house and if you don't have such anchorage systems, or if your structure is not so sound and all, then definitely there is a possibility of both injury as well as risk also. So let's try to be earthquake literates from now on. And yes, let me go to this particular provision of how to protect our architectural elements and utilities from earthquakes. What are the special provisions which we have in our latest code book and all? So again, this is a pictorial view of the upgrades which we have for 1893 2025. One thing is they have upgraded the zones. Typically, previously the zones were only 5. Now they have included one more zone. The inclusion of one more zone is like they are slightly trying to increase the amount of acceleration. I mean ground acceleration coming onto that particular place. and the proximity, like so you can see some statements over here. See, previously all this which is colored in dark red, extreme dark red, this was in zone 5. And even these parts of this city, these parts of Gujarat, even you have northeast as well as northwest also, which are in Gujarat. And Andaman Nicobar was also given in zone 5 previously, but now they have upgraded that to zone 6, which means some 70% of the acceleration will be is updated for this particular zones. I can see a lot of prompts here once. Is anyone adding, or is it from my side? Is my voice clear?
Yes, Karthik, it is clear.
Okay, I can see some prompts in here. Are people joining? Do I need to wait?
No, people are joining. No need to wait.
Okay. Fine. I can hear some
you can
ringing.
go ahead.
Okay, I can hear some ringing sounds.
That ringing is because like participants are joining.
Okay, I'll ignore them then. Okay.
Yeah.
Right. And then, as I said to you, now we have zone 6, and one more addition is the complete Himalayan belt, which has thrust faults and all. That has been also marked in danger, which means it is of zone 6. And a special provision was created for near field ground motions. Near field ground motions are typically ground motions which are collected at 20 meters or 20 to 30 meters from the fault. See, even for earthquakes, we have 3 sorts of assumptions. Earthquake can be assumed as a point source. Earthquake can also be assumed as a source, or earthquake can also be assumed as a fault source, which means the entire fault will get ruptured. The simplest assumption will be a point source, which does not hold that good to capture the physics of any earthquake. Line source is somewhat reasonable. But the best precise value in order to gauge an earthquake rupture scenario can be only to estimate the faulting as an area source rather than a line source. So, the ground motions near to the fault, let us say this is the nearest distance to the fault, and this is about 20 kilometers. In this particular vicinity, the ground motions which are generated from this earthquake has some very special characteristics like directivity and super shear. They are not like our typical earthquakes, which we collect some 200 kilometers from the fault range. Typically we collect earthquake data, seismographs from 200 kilometers or 100 kilometers from the fault range. They are a bit predictable, but earthquake in and around the source, especially in this particular buffer zone, 20 to 30 kilometers, the characteristics are very different. We have directivity, we have phenomenons like directivity, super shear and all. If you guys are interested in that, I can share detail on that. So this special provision has also been added. Of course, that peculiarity in this near field ground motions, it manifests in velocity pulses rather than acceleration and displacement pulses and all. And as I said to you, some big focus is given in this non-structural safety. All your architectural elements as well as your utilities, they come under these non-structural elements, and we need to safeguard them also. And additionally, some more emphasis has been kept even in the vertical component of ground motion. See, typically when there is an earthquake, you can collect the earthquake ground motion in all the 3 directions. For example, you have z-axis, you have x-axis, and then you have y-axis. Typically what happens is you have ground motion in x-axis, and you also have ground motion in y-axis. These two will cause the sway in your buildings. Your building is going to sway here and there because of this horizontal component of ground motion. And what about this vertical component of ground motion? Until today, we had an assumption this vertical component of ground motion is counteracted by the weight of the structure. But we have some special structures like pre-engineered buildings. We have pre-stressed concrete and all, where they behave in a peculiar manner, which means they even respond even to vertical components of ground motions also. So even this vertical component of ground motion is something which cannot be ignored. So good that they have included the vertical component of ground motions. Until now, we don't have that at all. And yes, I'll skip the last part. So this is what is the update in the present earthquake code. Now, and coming to the other updates in our earthquake code is they have introduced one good thing called as return period. Any earthquake is going to have some return period. Let us say you want to build a dam or something. The dam should, even post disaster, even after a disaster strikes at particular structures like your telecom towers, like your dams, like your bridges and all, they should be workable post disaster also. For that, you need to have a very high return period. And if you're building some temporary structures like your shed or some temporary warehouses sort of thing, you can go with a return period of 475 years. The thing is, if you're taking a higher return period, the amount of acceleration you need to design the structure is also very high. Let us say I want to build a temporary shed. You need not design the particular structure. Let us say you have a 6 magnitude earthquake whose return period is for 10 years. And you can also have a 7 magnitude earthquake. I'll just say a 7 magnitude earthquake which might have a return period for 100 years. And you can also have an 8 magnitude earthquake. The return period is slightly exponential. So you can have a return period of 1000 years. Now, the question is whether we need to build our structure for a 6 magnitude earthquake or for a 7 magnitude earthquake and for an 8 magnitude earthquake whose return period is for 1000 years. So what the code says is, if you're building special structures, especially which should be functional and operational after an earthquake, then you need to take a return period of 4975 or even much higher than that also, because the amount of acceleration it's going to attract is going to be that higher. For temporary structures, it's useless. It's waste of your money. It's waste of your time if you are actually building it for a huge return period. So temporary structures, you can take it as you need not even take it for 475 years. You can hardly take it for 72 years. And for permanent structures and structures with post-disaster importance and all, that can be given a very high return period. So a temporary structure, let us say if it is built for a ground acceleration of 0.5 g, which has a return period of 72 years, your bridges need to be at least designed for 1 g with a return period of either 475 or 975 and 2475. And if you're confused with what is the return period I need to use for my structure, you have tables for that. For example, you are actually building a liquid retaining structure. Let's say you are building some water, some petrol bunks, water retaining structure. You can blindly take a return period of 4975 years. So this is the kind of acceleration it might take. And if you are having some critical structures like your concrete buildings and all, you can design them for a return period of 2475. And some other, you can see over here also. See, this is the zone factor which we have. And look at the return periods. When the return period is for 75 years, look at the kind of accelerations we are taking. Even for zone 6, the acceleration is hardly 0.3 g. And for zone 2, it's going to be 0.03, which is just a rounding error over here. But just see, if you're actually increasing the return period, what is happening? It is slowly stepping up 0.3 to 0.35. And once the return period, let's say it's 975, it's 0.6. And look at the return period of close to 1000 years. You can have accelerations even more than 1 also. So if you are building your temporary structure, let's say if you want your temporary structure to last for even for centuries together, then you need to design it for lateral acceleration of 1.25 rather than 0.3. So this is what we do. So here your huts, your temporary structures, cape holes and all that, they can come over here, and your buildings can fall in these two categories, your residential buildings, and your hospitals and all can fall under these three categories, hospitals. And then your resilient structures, like emergency purpose sort of structures and all, like your bridges, dams and all, which will cause a secondary damage. Earthquake is a primary damage, but just imagine if it's going to break the dam and if it causes some flash floods or something like that, that's called as a passive damage. So if you are going to design such sort of structures, you better choose a return period of 4975 or 9975. And thus should be the accelerations also. Look at the kind of accelerations. It's even it's about 5 times more than what the acceleration obtained for 75 years. So this is some nice plot explaining you the return period. You can just extract it and see. And after a certain point, the curve also saturates, which means if you want to design your structure, let's say for 10,000 years and all, there won't be any amplification. The value saturates. It's going to be 1.125 only. Similarly, for zone 3, it's going to be 0.450 only. I'll explain a bit about return period if you guys are interested. But for time being, I'll go to the next slide. And Yeah, and the recent code, which is 1893-2025, it also has this site classification. You can see typically what happens is, if you are building your structure on soft soil, no, there will be amplification in your seismic waves, and if you are building your structure on rocks or something, there will not be any amplification. There will be de-amplification or attenuation. I just want to take, I mean, why should this site, the soil class or the site class need to be taken into consideration? We have it over here. You can see this is the, oh, I stopped sharing. Yeah, this is the notorious earthquake which happened in Mexico. You can see the epicenter over here. And you can also see the accelerations. It's hardly 150 centimeter per second square. And when the wave has traveled all the way from here to Ticaclo station, you can see that it has completely attenuated. From 150, it has come down all the way till 18 centimeters per second square. But the moment it has reached the Mexico City, which is constructed on a huge bin, the Mexico City is completely constructed on a huge bin, which is made of soft soil. It has, I mean, until here it is hard rock and all, but the Mexico City is constructed on a very soft soil, and suddenly there is amplification in the seismic waves. And you can see over here the kind of amplification we have observed. From 150, it attenuated to 18, and from 18, it has increased to 170. That's the reason the soil condition on which you are building your structure should also be taken care. All thanks to our latest code, which has taken this particular scenarios into consideration, and it has given us even the soil categories also. You can look at how this particular bandwidth has been slightly spread. If the site class is from A to B, where you typically have very dense rock or dense soil, these are the only structures with time periods which will attract accelerations. But if you are actually you're building your structure on a very soft soil sort of thing, there is a possibility even structures with higher time period will also attract equal amount of seismic forces and all. So it is like, basically people treat structures in two ways. One is acceleration sensitive structures, the other one is displacement sensitive structure. Let us say you have a structure with short time period. What happens is, if this is the structure, and sorry for my rustic writing, I have this pen but it's not working. And if it is hit by an earthquake, let's say this is a very short time period structure and it's a very stiff structure. When it is hit by an earthquake, there is a possibility that it might only attract it is acceleration sensitive, which means it might only fail by toppling and all. But if you have a displacement sensitive structure, so let's say you have this tall structure which is displacement sensitive, what happens is that the mass might stay there, but the support will actually try to wobble here and there. These are called as displacement sensitive structures. So for a structure to be displacement sensitive, its time period should be extremely high. So in our engineering seismology, we classify structures as, a short time period structures, which are acceleration sensitive, and long time period structures, which are displacement sensitive. You can actually precisely even, gauge the displacement in this sort of structures. And there will be some mid-rise buildings which are velocity sensitive. So acceleration is going to hit short structures, velocity pulses are going to hit moderate rise structures, and tall structures are displacement sensitive. So this is how we classify the structures and all. So the site classification has helped us to broaden this one. See, if it is a very soft soil is going to influence even low-rise buildings as well as moderate-rise buildings also. That's why we have that bulge in that particular curve after reaching the plateau region and all. So this is one nice emphasis which has been made in the recent code, as I said to you. And now coming to the topic which we are going to discuss today, we will be dealing with non-structural elements. As I said to you, these elements are only for aesthetic purpose and just to fulfill your functionality, which means there is a fridge in your home. That the very purpose of the fridge is to air condition your food materials and all, and to avoid spoilage of that particular material. But does it act in load transfer and all? No, it does not do that. It's not a beam, it's not a column, it's not a slab and all, but it's going to stay in your house. So such sort of structures, such structure sort of functional materials are actually called as utilities. You have a vent running in your home. That vent also does not participate in load transfer, but still it should be operational even pre and post earthquakes and all. And these days, people are glorifying their homes like anything. They are minting in a lot of money to improve the elevation and all. They will have some cladding material. That cladding material is fixed to these structural elements, but don't know how safe are these cladding materials, don't know how safe are these utilities and all. See, and what comes under these architectural elements and utilities? You can see over here your furniture, that also comes under utilities, your equipment, any machinery you have inside your home, like your conditioners, your fridges, your washing machines, your book rack, even your cupboards, which are not integrated into the wall. All these can be treated as utilities. And architectural elements, you have parapets, you have ceilings, you have false ceilings, you have verniers, you have partitions also. And you also have some service utility equipments like HVAC, heating, ventilation, and air conditioning, all the electrical plumbing works, even systems. You have a dish, you have some dish, or you want some satellite channels and all. All of those can be treated as utilities. So what is our objective regarding these utilities? These utilities should not be damaged. See, because you might be spending some money to retrofit your structure, but just imagine, your expensive vase, or let us say your plumbing system, it completely gets destroyed. Perhaps retrofitting a column hardly takes 25 minutes, but for the plumbing to be set aside, just imagine the entire plumbing system of the building is completely broken during an earthquake. It's going to take, at least, see, we cannot really afford those days. The plumbing system should immediately work, right? You have cooking to do, you have some other purposes. You need water, you need to wash your clothes and all. They are commodities should immediately work even after an earthquake. So we cannot really afford the 28 days for these utilities and all to be functional even after an earthquake. And one more thing is, sometimes the structure is going to be extremely sound and it's going to withstand an earthquake, but what happens is the false ceiling is going to be faulty and it's going to drop on our head. We can also have death is unpredictable, and because of these utilities falling on us, we cannot escape that sort of injuries. So that is why special provision has been created on that. So what he says is, according to this particular codal provision, he wants all the utilities and even this architectural elements to be integrated nicely with the structural element. So what he says is, he says that any structural element, you have a structural element, it should be earthquake resistant, and he wants the non-structural element, NSE, to be also integrated with the structural element, which means he want to anchor this non-structural element to structural element, such that the inertia, you might have studied in your physics, there is any force, any body which is in dynamic motion will always experience inertial force. That inertial force should be transferred to the structural element. You might have experienced inertial force while traveling, in a train or in a bus. You always hold that particular, you have a belt sort of thing which you hold it. Why? Because you are transferring your inertia to that particular belt, which is integrated into the structural element. Just imagine you are not holding the particular belt, you will fall off. The same thing is going, or you are going to fall on your neighbor. So that the same thing is going to happen even for your non-structural element when they are not integrated with your structural element. And how do you integrate them? You need to anchor this non-structural element to your structural elements and all. So I'll explain. Yeah. So what are these non-structural elements? As I said to you, again, a pictorial representation. The water tank, the high density plastic water tanks. We have Syntex water tanks and all. That also comes under non-structural element. The pipings and all will come under non-structural elements. Whatever you have, your cylinders or your ACs or your televisions, the pipes which are running from top to bottom, or the hoardings which you typically rent your, the terrace of your house, you rent it even for boardings, especially in metropolitan cities and all. They rent all the terrace to hoardings and all. They're going to pay some amount, and sometimes even the terrace is rented even for transmission line towers or cell towers and all these things come under non-structural elements. You can see over here. And even the cladding of your building, you can see over here. The building will be aesthetically appealing when we are looking it from outside. You can see all the Chennai buildings or Hyderabad buildings, all the software buildings and all. I mean, you have glasses outside, but don't know what happens if this particular glass is not properly anchored onto your structural element. The glass falls on our head, or the complete glass is broken. Just imagine how much money and time we need to invest so as to repair our non-structural elements, rather than just providing one bolt or two bolts just to anchor them properly. They say, right, there is a saying, a stitch in time saves nine. The stitch here is your anchorage which you cause between your non-structural elements and your structural elements. And here are some more examples of your non-structural elements or utilities. Your filling cabinet, your multi-storage racks, your parapets also. There are lots of cases when earthquake happens, the entire moment resting frame is going to stay intact, but the infill walls and the parapet walls are completely gone, and they need to reconstruct the walls. The only way we can do is we need to anchorage these particular walls into your structural elements. and sometimes even the brick chimney goes off. Of course, elevator. There are lots of cases where the elevator has completely collapsed during a disaster. The frame will be intact, but elevator, there is no special provisions for that. That's the reason the engineer has not taken any concern about that, and it's completely gone. So this is how your non-structural element looks like. And these are the possibilities. What happens when you don't anchor your non-structural element to your structural element? You can see over here, there will be some hanging or some fan above your head, which is displacement sensitive because it has a longer time period. As I said to you, it's not acceleration sensitive, it's displacement sensitive. And it's going to swing a lot. And if it is not properly anchored, it comes and falls on our head. The earthquake did not kill us. Actually, we sitting under that particular fan, it's going to cause some head injury or something. Or you might have some huge book rack or something, and it is acceleration sensitive. Equipment and all, they typically fail by sliding. I'll show you more schematics in the coming parts and all. Or you might have some glass gazing over here. What happens if your cupboard is not properly anchored? When there is an earthquake, there will be inertia force. The whole building will move in this direction. This particular thing, which is not hooked onto the floors, will be moving in this direction. And after some time, it's going to topple out, and it might cause some risk. So this is how. And why again? Why do we need to emphasize on this? Non-structural elements or this architectural and utility elements? Because first thing is 61% of the Indian population is under earthquake, and second thing is the population density. In this 61% only, many people are living. People won't be living in some Rajasthan deserts, or people will not be. The population density is quite less in some places which are not comfortable for us to live. We live in a place which has all those functionality, which has the IT hub near to you, which has some refreshment park and all. Their population density is going to be extremely high. Unfortunately, the population, wherever you have population density, the same region is prone to earthquake also. Now just imagine what kind of precautions do we need to take to address this particular population density. Landmass may be only 60%. Rest 40% is there. We can live in that 40%, but we don't choose to live in that 40%. So what are we doing? That 40% has been reserved only for 25%. And the 75% of the population has moved to the 61%. The rest of the earthquake prone areas. So this is why we need some special emphasis on this, again, as I said to you. And one more thing is the money involved. I don't know whether you have experienced this or not. We take EMIs and buy some air conditioners. Just imagine that air conditioner being completely hooked from that particular place and falling it down. And the technician will come and say, this is beyond repair. You need to purchase a new air conditioner. How many EMIs will you sacrifice? And just imagine the kind of money you are keeping to build your home. Let us say you are building your home for 30 lakhs or 40 lakhs or something. You will at least invest some 10 to 20 lakhs, for these utilities, in the sense for your air conditioner or for your plasma televisions, 55 inches, or your two-door fridges which you have, and your costly wardrobe. All these things, they also account at least to 50% of how the money you have. You minted onto the structural elements also. So first thing is money. It's going to boil a hole in our pocket if you are not bothering to buy that particular screw to anchor the non-structural element to your structural elements and all. And okay, residential houses and all, we are okay to take up we are okay to take up the expense. But what about hospitals and data center? You can see, you might have visited some ICU, intensive care unit. Just imagine the kind of equipment which will be surrounding the particular patient. He has some large equipment surrounding him. Now, if these equipment is not properly anchored, forget about saving that patient. That patient is going to die because of this particular, equipment falling on him. So even those things should also be properly anchored. And sometimes, equipment will be toppled. There might be some rupture of pipings also. Parapet might also fall down. And second thing is the time taken for you to relapse. As I said to you, keeping back these non-structural elements, especially these pipings and all, is going to take much higher time than treating your structural elements. So here is your downtime which you have to construct it. So if structural element hardly takes some 25% of your time to repair and rehabilitate it, a non-structural element is going to take some 70% of your time. So if you are not convinced why we need to anchor your non-structural element with your structural element, just imagine these two things. First thing is it is targeting your investment. Second thing is it's targeting your time also. And money and time are the most important priorities which we need to choose in life, I guess. Now, coming to What does our codebook speak about these things? See, our codebook has classified these utilities and architectural elements under 3 types. Architectural elements and utilities can be classified as acceleration sensitive, they can be classified as displacement sensitive, or they can be classified as both acceleration and displacement sensitive. So what is this acceleration sensitive? What is displacement sensitive? I'll just highlight in the coming slides. You see over here, you have this particular mass, just imagine that being a fridge or being a heavy cupboard or being your television or which is kept on a cabinet or something. When your structure is being hit by an earthquake, there is a possibility that this particular fridge will slide. And what happens when it slides? Let's say that particular fridge is something like this, and when your earthquake actually tries to move your floor in this manner, there is a possibility that this particular fridge will slide. If it slides, it's okay, you can move it back to its original position. But what if it topples? And you have a kid under it? Just imagine. We cannot even imagine such sort of situations. You might have done this toppling mechanics for your retaining wall. Do you remember how you design your retaining wall? You just don't design the stem as well as the heel or the toe. You also design the retaining wall such that the retaining wall does not topple. Do you remember that? Rajaram sir, can I expect some response from the audience?
Yes.
Yeah. Okay. Or shall I proceed?
Yeah, you can proceed.
Fine.
Sir, proceed, sir. We are listening. Don't worry.
Okay.
Thank you.
Okay, fine. So acceleration sensitive equipments are they fail by the sliding or toppling mechanism, whereas displacement sensitive equipments, let us say your pipe is being connected from the bottom story to the top story, then what happens is there will be some relative displacement between top and bottom story. This relative displacement will actually cause a tear in this particular pipe. Got it? It will cause a tear in this particular pipe. So acceleration sensitive equipments are typically rigid they undergo rigid body motions, which means they won't have they won't have internal deformations. But whereas displacement sensitive equipments are going to have internal deformations, rigid body motions. In engineering mechanics, we have the concept of rigid body motions. So I mean, you can try to keep a bottle on your table, water bottle on your table, and try to shake the table. What's going to happen to that water bottle? It's just going to topple. Such sort of toppling behavior is called as acceleration sensitiveness. And let us say you have some let us say you try to tie your table with some string or something, and if you try to move that particular table, the string gets snaps off. Such sort of behavior is called as displacement sensitive behavior. And there might be some equipment which is both acceleration as well as displacement sensitive also, which means the equipment is going to be heavy, it's going to topple. At the same time, it's going to have even as I said, snapping of these particular compromising on the integrity of the equipment will also happen. So these are the 3 categories which we need to classify your architectural and utilities so as to go with the appropriate design and all. So now let us stick to this acceleration. Maybe I'll show some images, then you can understand what's meant by acceleration sensitive and displacement sensitive. You can see over here this particular image. See, you can see the kind of failures over here. The failure is either due by sliding or toppling, or maybe I'll show the acceleration sensitive. Yeah, you can see the failures in here. Can you observe this one? It is swaying actually, but is it like the integrity of the entire equipment is properly maintained? The material as a whole will actually topple in this direction or in that direction, and there won't be any internal deformation in between the material. So this is actually called as swaying. You can see even the arrow marks will denote the possible chances of impending motion. You can see over here, and the equipment might also slide. You can see over here it's actually sliding, and this is when the equipment moves away from each other, when the toppling is in the backward direction, and this is when it has completely collapsed. So this is going to happen, and you can see what's going to happen. This is also an acceleration sensitive equipment. You see, we call it as ASE, acceleration sensitive equipment. But whereas if you have a pipeline running from bottom to top, this particular pipeline will not have this rigid body motions. They are displacement sensitive rather than acceleration sensitive, which means if this particular story is displaced by, let's say, 0.01 mm, and this particular story is also displaced by 0.01 mm, it's not going to cause any damage to this particular pipe. But if the difference in these displacements, interstory drift, is very high, then it actually causes the tearing of that particular pipe. So you properly need to classify what equipment is acceleration sensitive and what equipment is displacement sensitive. What is the protocol to safeguard that acceleration sensitive equipment against earthquake, and what's the protocol we need to follow for displacement sensitive equipment. I hope it's clear to you what's meant by acceleration. For example, let us say you have an infill wall. Sorry, you have a frame, something like this. It's a two-story building. You have a frame like this, and let's say this entire thing is completely covered with glass. See, typically glasses are not ductile elements, right? They are brittle in nature. The backbone curve of the glass is going to be like this. Brittle elements will have a backbone curve like this. Ductile elements are going to have some reserve of stress, which we call it as plastic region. This is called as reserve of stress. Get that? So this, let us say, earthquake has hit this particular building. What happens to this building? The deformation of this building is going to be in this manner. You can see over here, it's going to be like this. But the building might have some sufficient ductility, but the glass will not be ductile. So what happens is the glass fails. And why did the glass fail? Because the displacement over here as well as the displacement over here are compromised. There will be some relative displacement between these two. So glass should be treated as a displacement sensitive, not acceleration sensitive. So something which is affected, which is influenced by relative displacement or relative displacement equipments, and something which exhibits a rigid body, response is called as acceleration sensitive utilities or equipments. I hope that classification is clear to you. Okay. Let me just go back to my slides. And so yes. Now coming to how to design the anchorages for this acceleration sensitive equipments. See, you have some factors which you need to follow in here. So this is the formulation which was prescribed for your code book. Z is typically the zone factor. See, typically you can adopt this particular zone factor from the structure. While you are designing the structure for earthquake resistant design, you will be having some zone factor, right? The same zone factor can be placed even here. And I plus x by h. X is typically how tall is the structure, the equipment placed relative to the structure, which means let us say your structure is some 20 meters. The entire length is about 20 meters. Let us say you have placed this equipment somewhere at 10 meters. Here you have placed that equipment. X will become 10. So this is 10 meters. So X will become 10 and H will become 20. So what happens is this is just a height amplification factor. Higher is the value of X now. So now what is the value of X by H? It's 10 by 20. 10 by 20 is, how much is that? 1 by 2, it's 0.5. So the height amplification factor is going to be 1 plus 0.5. So the overall factor you are going to take is how much? It's going to be 1.5. So this is a height amplification factor, whatever X by H is there. Let us say you are keeping your structure, let us say some 2 meters from this particular ground level. So the X by H value will be 2 by 20, which will be 1 by 10, and this 0.5 will be 0.1. Because so it becomes a de-amplifying factor. You are hardly taking 10% of whatever is the zone factor which you have here. And I, as usual, is the importance factor. Typically, if it's a, let us say, see, if it's a server room or something like that, or if that particular equipment is holding some hazardous material, let us say some nuclear waste or something like that, that sort of equipment should be properly anchored, and it should also have an importance factor, because we cannot afford toppling of that particular equipment. You can see the importance factor is similar to the importance factor you are giving to the buildings, but here you are giving the importance based upon whether it is extremely hazardous or not. A fridge falling down, that's okay. It does not omit any hazard except fluorocarbons. But just imagine a silos which is storing a nuclear waste being toppled and falling down. It actually creates a nuclear hazard. That's why you need to increase the scale of the force, the anchorage force which you are designing. So typically, if it's an ordinary equipment, you can just take the importance factor as 1 and you can go ahead with it. And then you also have something called acceleration amplification factor. What he means by acceleration amplification factor is, I just, Rajaram sir, am I juggling between slides, or is it okay? Like if I go to and fro with these contents? Okay, let me just explain you. Now see, we have completed the variables Z, I plus X by H. Now we also spoke a bit about the importance factor. Now we have force reduction factor, which you are calling it as R, we also have an acceleration amplification factor also. Why are we talking about this acceleration amplification factor? You see this particular image. You see this particular image and see ground motion. Look at the amplitude. The moment ground motion reaches to the soft surface, to the top surface, look at the amplitude. It will be slightly increasing. But look at the response of your system. This is the non-structural element, and look at the response of your system. Can you see it is even more scaled up? So this is the ground motion, which is scaled up when it is reaching the top structure, and it is even more scaled up. So this particular amplification needs to be taken into consideration. I'll just mark it for here. You see this particular amplification, the difference between this as well as this particular amplification needs to be taken into consideration. So for this amplification to be taken into consideration, you have this factor, which we are calling it as acceleration factor. You have it over here. This is the acceleration factor which we have. So you just imagine the how over conservative our code books are. You have an amplification related to height. You have an amplification which is also relating to height, and it also depends upon as I said to you, the equipments are completely acceleration sensitive. They are sensitive to ground accelerations. That's why you have these amplification factors and all. And there is one more under conservative values also. You can see over here. We have a reduction factor. This reduction factor is to typically not to over strengthen the anchorage systems and all. See, you might have heard about this reduction factor even while you are designing your structures based upon equivalent lateral load method also, ZI SA by G by 2R. That's actually called as response reduction factor, but here we call it as elastic force reduction factor. What he means is any ductile material will typically behave in an elastic manner until one particular point, which you are calling it as yield point, and it will going to have some plastic strains. Then on this particular strength is actually called as the ductile strength of a material, and this particular strength can also be utilized. Let us say you have your particular screw like this. Even if it is deformed, it does not mean there will be rupture in that screw. It can deform until certain point. All you will have is only the neck formation in this particular screw. You have a neck formation like this. Just because there is neck formation does not mean this screw has completely lost its functionality or utility. Even if there is neck formation, still it can take up this particular load. It cannot take up load only when there is fracture in that. So you can go all the way from here till here, and from here on, you will have a post collapsing cap, and then it goes off. You cannot go till this particular point, but you can take advantage of the displacement till here. So that inelastic behavior should be taken into consideration. That's why you have this reduction factor, which will help us to underestimate the amount of forces coming onto your structure. So this is how the value is, and the entire factor needs to be multiplied with the weight of your equipment. Let us say the weight of your fridge is, let's say, 100 kgs or something. Convert that kg into newtons. It will be 1000 newtons, and the 1000 newtons should be multiplied with all of these factors. And if it's more than one, it's going to report some 1100 newtons or 1200 newtons or something. Based on that, you need to design your anchorage. So this is how you design your acceleration sensitive equipments and all. Sir, shall I stop for a while here, sir? Do I need to does anyone have any questions or anything? Hello, does anyone have any questions?
You can continue the presentation, sir.
Okay, fine. So there are some calculations which I have included to find out how do you provide the anchorages and all. Like I am slightly running out of time. It's 2:50. That's okay. I'll just skip this particular part of calculations. Maybe if time permits, I'll come back to it. And yeah, again, I am reintroducing the topic to you. Acceleration sensitive body motions. Displacement sensitive is something. You can actually have a feel of the displacement. That's why we call them as sensitive. Just imagine your structure is being hit by an earthquake. The chandeliers, or the huge lamps and all, or if a tube light is being hung by a string, they are displacement sensitive and they are subjected to sway also. And sometimes there will be equipment which is both acceleration as well as displacement sensitive. Look at this particular water tank, which is situated on some sort of frame. The water tank is acceleration sensitive, but whereas the particular frame is displacement sensitive. Perhaps the ground motion here, ground displacement here and here might be different. That's why this has reacted to that, and it has it has yielded. So this is how we classify the equipment and acceleration, displacement, and acceleration from displacement sensitive. And this is some special provision which is new added. We also have they included some special interest on near field ground motions also. You can see this is the standard spectrum which we have, and because of near field ground motion, it is slightly scaled up. But typically, there are these people like from USGS, Somerville and all. They extensively worked on near field ground motions. They have some Pacific Earthquake Engineering Center reports also, reports exclusively for these near field ground motions, how to make your response spectra, slightly mutation to these near field ground motions, where to exactly bulk up your spectra, where to narrow down your spectra, and all these things are covered by him. Good that special emphasis has been brought by this particular code book about near field ground motions also. But still, it's an enchanted area. It still needs to be explored a bit. And yes, you can see why displacement sensitive, as I said to you, it will cause brittle failures and all. Thus, the frame which is holding our equipment can be can withstand the relative displacement, but the thing is it might be hosting some glass, and the glass is ductile in brittle in nature, and it cannot hold up this relative displacement and all. And even this piping things also, the piping is also, there might be some tear off in the pipes also. And second thing is it is extremely costly to replace them and all. Now, how do we take care of this, the relative displacement into consideration? As I said to you, this is how we calculate it. You just need to take the difference between between the interstories, which means, so this is the difference in displacement, and somehow your pipe needs to be some special arrangement needs to be made in your pipe to accommodate that particular relative displacement, and the formulations will be just the relative displacement multiplied by your reduction factor. As I said to you, we are taking the advantage of the structures over strength also. The reserve of strength, we are taking care of that, so that multiplied by the relative displacement which you have. Sometimes if you are having a piping system running in between two buildings, two adjacent buildings are there, and your piping system is running in between them, what you need to do is this particular thing goes in this way, and there'll be some displacement even there, and the displacement is going to be the absolute sum of both the displacement, which means this particular story will go in this direction. Let's say it's 0.2 mm, it's 0.2 mm. The overall displacement is going to be 0.4 mm. And sometimes the pipe might be directly connected to the ground. When it is connected to the ground, you have a factor called 1.2 that should be multiplied with ground displacement plus the story displacement. So this will be the overall displacement. You need to design the pipe for this extra displacement, or you need to create a special provision in that particular pipe such that it can actually elastically expand for this particular displacement. I'll show you. There are a lot of vendors in the market who can give that ductile material to be used as pipe fittings and all. Yes, these are all the displacements which we have. I'll just skip this particular part. Yeah, let me talk about this one. See, how to protect your AEUs, architecture equipment and utilities. You have three methods for that. You have one non-engineering method, you have some pre-engineered method, as well as you have engineered method. This is how your non-engineered method looks like. Let us say your vessels or your plates and crockery plates, which are typically brittle in nature. You can actually run some run some cables and all, and you just need to confine them such that even though if they wish to topple, we are still trying to arrest their movement. That's how you can do. But this is a very primitive in nature, and it's a non-engineering way of doing things and all. And sometimes you can also do some pre-engineered ways, like let's say you have that equipment, you just need to have hooks all around the equipment, and you can start holding them, just like your guide chimney will be there, right? Just like that, you need to anchor them properly. And if you call me, this is the latest method which we have, which is called as engineered method. Your equipment will also have that slots, your building will also have that slots, and all you need to do is you need to anchor them together. See, for example, this is the structure you want to design, and let's say you got a force which is parallel to the structure. Let's say you got some 100 kilonewtons. You just need to divide it among all the anchorages. Let's say this will take up some 25, and this will take up some 25, and this will take up some 25, and this will take up some 25. So whatever is the lateral load coming on to that particular story, that factor multiplied the weight of your structure, and the anchorages should be designed based upon that. So This is the order of the day as of now, where people are selling their products saying that they are earthquake resistant and they are going to be nicely anchored even in your home. And even if there is an earthquake, these non-structural elements are not going to cause any damage, and they are, that's how they are selling it. You can see over here the structural element is going to be stay intact, but what takes up most of the area is your non-structural element, the vents, which are, you can see the AC vents, HVAC vents, as I said to you, heating, ventilation, and AC vents, HVAC vents, and all. You can see over here, even this false ceiling and all. This is again displacement sensitive, and these are all acceleration sensitive. This particular thing and all. This may, make up a lot of those parts. And this is what I have said. As I said to you, there will be some relative displacement which you need to accommodate. For that, you have this sort of special equipments and all. Let's say you have some piping in here. Both the pipes should be added with this particular joint, and this is an expandable joint which you have, and it can take up some displacements of even 0.5 meter also it can take, which is extremely huge. So this sort of, or else you can actually take some some bendable pipes into consideration. They are made of some special alloys where they can nicely bend, even if this particular wall is going in this direction and this wall is going in this direction, still you have this whole bend to take care of the relative displacement. And sometimes what happens, you can also have this sort of equipment also, where the pipe is made to fit on this particular slider. You can see the slider. So what does this slider do? This slider actually slides, in this way. So even if the building is sliding here, and the building is moving here and there, the pipe will take the help of this particular slider and will try to slide both in this way as well as in this direction. In that way, the pipe rupture will not happen because it's acceleration sensitive. And then you can use this sort of anchorages. You see, you can have this tripod anchorage over here. With that, you can hold your you hold your pipes and equipment also. The anchorages are extremely strong, and as I said to you, the inertia should be transferred to structural elements. So how did he transfer? These pipes will have some inertia. That inertia is transferred to this particular node, and from this particular node it is transferred to the structural elements. All these are structural elements only. You can have them over here. And this is some, these are some anchorages which you can have. And this, so see, they might not take a lot of money even to invest also, but the thing is, if you really want to replace this pipe after it is completely ruptured, that actually is going to take hell lot of money. So it's better to stitch in time. That's what I'm saying. These are the kind of anchorages we have, and you can see how nicely they have anchored it here. And the kind of material you pour into the anchorages is also not that high compared to the material you are pouring into your reinforcement and all. And these are some special anchorages which can extend also. They can extend, means they are displacement sensitive. After a certain amount of displacement, they dissipate the energy. How do they dissipate the energy? They displace and dissipate the energy, but the displacement will not cause any tear. That's how they do it. And of course, you can see over here, can you see this one? These are anchorages which are provided. The bolt either need to be designed in tension or in shear or both, and then you can do it. So yes, sometimes we have this sort of damages also. You can see over here, they did not take the stiffness of the infill wall into consideration, and that's why you have the stress transfer is slightly different. So you have this sort of damages. And see this particular water tank. This water tank, when you are designing, it should be treated as non-structural element. Has this been a structural element? Why is it not participating in load transfer? It is not properly anchored. So the entire building might be intact, but the water tank came down and it toppled itself onto that particular building, causing the failure of that building. So, and as I said to you, there are three methods. You have non-engineering methods. Where is that? Yes, you have non-engineering method, pre-engineered method, and engineered method. I'll show you some non-engineered method which people were using during the Loma Prieta earthquake and all. So he has nicely cased these battery cells and all by using this non-engineered method, or pre-engineered method, you can say that. And what happens when you don't case them? This is what is going to happen. This is during the notorious 1971, San Francisco earthquake. This is what has happened to the battery bank. It has completely fallen down. And look at this one. This is nicely anchored and it is kept in a case-like manner, and it is not, it's not damaged at all. And look at the racks. You can see over here. This is, you see, do you call it as acceleration sensitive or displacement sensitive? It's both acceleration and displacement sensitive. What I feel is, it might have slided a bit and then it might have relative displacement. You can see over here, they had relative displacements. No, this diagonal portion, it's long, and that might damage your frame and all. And when it is not properly tagged, this is what is going to happen. And this is during the Withers Narrows earthquake. And you can see over here, when they are not properly stacked, you can, and this is, can you see some non-engineering equipment? I mean, procedure is there. All the bottles are actually, there is some string which is passing through, some small cable. I don't know whether you can see that or not. That's the least we can do. That's a non-engineering strategy which we have. That's the least we can do. Or even, and this is how, your lights or your fixtures, they were being destroyed. Look at the kind of asbestos we have, that false ceiling and all. And the weight of the false ceiling is also not less. It will be some 0.5 kilonewton per meter square, or it will be 0.25, which is not that light. Just imagine it being falling on our head, and it's not properly anchored and all. And even these particular tube lights, which are not properly anchored, or he might have compromised on the number of nails and all. And this has also been damaged during the 1893 Kolinga earthquake. And then you have, yes, this is what I was talking about. This is called as displacement sensitive. I hope you can see my pointer. You can see over here. So what do we need to do here is, you need to have some special equipment over here which can expand, which can take up that amount of displacement also. If you are going to enforce that, then both of them will be like this. Perhaps after the earthquake, then they will slowly have the self-centering behavior, and they will come back. And coming to how much are we investing in this non-structural elements, you can see over here for India, until 1950, we were investing only 20%, but from then onwards, you see 70% we are investing in non-structural element. Just imagine the kind of money it's going on, which means if you're spending 1 crore on your house, including the interiors, including the equipment and all, 30 lakhs will go for that structure which you are building, and 70 lakhs will go for all your, for all the other things, like your ambience, the lights, the expensive vases, and all these things you are buying. It's happening. Of course, that culture has been there in foreign countries for long. They are gaining even more momentum. They are spending some 90+% on this, non-structural elements and all. And this is a rough, just to eyeball how much are people spending on non-structural elements. You can see the yellow tag is a non-structural element. For hospitals and all, you have lots of non-structural elements. 44% has been spent. For hotels, 70. For residential, it will be some 20 odd or so. So should this be given some preference? Yes, it definitely should be given some preference, because its participation is also that high. Yeah. Here you have some sliding mechanism where the pipe is being run behind the building, and this level of slots are typically given, so that the pipe will try to will juggle in between this slot. The slot, it just like your slot bolt, you will let the bolt to slip, right? Just like that, you need to let it to slip. So